Every time you click a link, you're kicking off this insane high-speed relay race across the entire globe. In the tiny fraction of a second it takes for a web page to load, a tiny piece of your data travels from your screen, maybe to a server thousands of miles away, and then all the way back. Today, we're going to follow the incredible journey of just one of those data packets. So what really happens in that blink of an eye? It's a journey that has to navigate through dozens of different devices, speak multiple digital languages, and even pass through security checkpoints, all in just a few milliseconds. Let's trace that path, step by step.
Okay, so first things first, your request for a website or video doesn't just travel as one giant file. That would be way too slow and super inefficient. Instead, your computer acts like a digital shredder, chopping up all that data into thousands of tiny, manageable pieces. Each one is about to start its own little journey across the internet.
And each one of those tiny pieces gets put inside something called a data packet. This packet is the hero of our story today. You can think of it like a digital envelope. It's got a little piece of your data inside, a destination address telling it where to go, and crucially, a return address so the response knows exactly how to get back to you. All right, our packet is all sealed up and ready to go. Its very first move is to leave your computer and enter its immediate neighborhood, your local area network, or what we call a LAN. This is just the private network that connects all the devices inside your home or your office. And that first step is a physical one. Most of the time, it's through that good old Ethernet cable plugged into your device. This wire carries our packet on its very first hop, sending it to a central connection point that handles all the local traffic. That central point is a device called a switch. The best way to think about a switch is like a super efficient mailroom sorter for your local network. It looks at the local address on our packet and knows exactly which desk, or in this case, which computer or printer to send it to, making sure it doesn't bother any of the other devices. And this precision is a huge leap from the old way of doing things. Before switches, we had these things called hubs. And a hub? Well, it was like a town crier. It just shouted every single message to every single device on the network, creating a ton of noise and congestion. A switch is so much smarter. It's like a private messenger. It reads a special hardware address called a MAC address and delivers the packet only to the right recipient. It's incredibly efficient. So our packet is now zipping around the local network. But to go any further, it needs a complete address. It needs to know not only its final destination way out there on the internet, but also exactly how a reply can find its way back home. This is where the internet's own GPS system kicks in. First up, every single device that can connect to a network has a MAC address. Think of this as its permanent physical fingerprint. It's a unique serial number that's literally burned into the hardware by the manufacturer, and it never, ever changes. It identifies your specific laptop, no matter where it is. But that MAC address is really just for local delivery. To navigate the whole internet, our packet needs a different kind of address, an IP address. And this is where a service called DHCP comes to the rescue. When you connect to a network, a DHCP server automatically lends your device a temporary IP address. It's kind of like a hotel assigning you a room number for your stay. It's not permanent, but it's the absolutely crucial return address for our packet for this trip. Okay, so we have a return address. Fantastic. But what about the destination? See, we humans use nice, friendly website names, but computers, they only communicate with numbers, those IP addresses. DNS, the Domain Name System, is the magic service that handles this translation. It is literally the phone book for the entire internet. You give it a name, it gives you the right number. And this all happens through this lightning-fast, totally invisible conversation. Your computer basically shouts out to a DNS server, "Hey, what's the number for example.com?" The server instantly looks it up in its massive directory and replies with the correct IP address. And with that final piece of the puzzle, our packet is fully addressed and ready to hit the road. So, let's take stock. Our packet is fully addressed, it knows where it's going, and it knows how a reply can get sent back home. Now it's ready to leave the cozy local network and merge onto the global superhighway of the internet. And this is the job of a router. Now, if a switch directs traffic within a single network, a router is the traffic cop at the giant highway interchange, directing packets between all the different networks. It reads the destination IP address on our packet and makes a decision about which path to send it on to get it one step closer to its final stop. So let's make this super clear, because this is one of the most important concepts in networking. Switches, they connect devices on the same local network. They're all about the local neighborhood. Routers, on the other hand, are the bridges that connect different networks together. They're what build the global internet we use every single day. That's the crucial difference. Our packet is now hopping from router to router across the vast internet, getting closer and closer to its destination with every single jump. But along the way, it's going to run into some serious security checkpoints that are designed to keep networks safe. And this checkpoint is the firewall. You can think of it as the digital security bouncer for a network. It stands right there at the border, inspecting every single packet that's trying to get in or out, and it checks their credentials against a really strict list of rules. And this table right here gives you a great idea of how a firewall thinks. It uses a set of rules called an access control list, or ACL. It looks at the packet's source, its destination, and even what service it's trying to use. If the packet's details match an allow rule, great, it passes through. If it matches a deny rule, well, it gets dropped on the floor. But what happens if a packet doesn't match any specific rule? Well, that's where the most important principle of firewall security comes into play: implicit deny. It just means the default answer is always no. Unless a rule explicitly says you can come in, the packet is blocked. It's a guilty until proven innocent approach, and it's what makes networks secure by default. So our packet has been created, addressed, switched, routed, and inspected. It has successfully navigated all the complexities of the global network, and now it's finally arriving at its destination. The destination server receives our packet along with all the other packets that made up your request. It assembles them, processes everything, and then it prepares a response. And that response, the web page you wanted to see, is immediately broken down into its own army of packets, which instantly begin that same incredible journey, just in reverse, all the way back to you. So let's just recap that entire whirlwind journey. In just a few milliseconds, your single click created a packet. A switch directed it locally. DNS gave it the destination address. A router sent it across the entire internet. A firewall checked its credentials, and it finally arrived at the server. It's this incredible, coordinated dance performed by billions of devices every single second. But here's a final thought to leave you with. We've described this journey using physical hardware, cables, switches, and routers you can actually touch. But as more and more of our networking moves into the cloud, with virtual switches and software-defined networks, how might this journey change? The principles, they're still the same, but the path itself is becoming more abstract and more dynamic than ever before.